In this video, we're going to look at viscoelasticity. So when we looked at viscoelasticity in previous lectures, we looked at it in terms of a damper. So we took a damper and said that it has a damping coefficient that could be uh, dependent on the rate of change in length. So the force developed by this damper is equals to some damping coefficient times the, if this is the change in length and it's represented by x, let's say, then dx dt. So it's linear with respect to the change in length. Now, just like with the spring, we want this to be not a property of the dimension, actual dimension of the material, but some kind of intrinsic material property. So for the spring, we use the elastic modulus, and we derive the equivalent spring constant for a material of given elasticity and cross-sectional area and original length. So given a elastic modulus, we could calculate the equivalent spring constant for any material. So this concept, extending this concept is a little bit more complicated for viscoelasticity, but what we'll do is force, if we divide by area, then we'll just get stress, and instead of this being now a damping coefficient, so this, we call this the damping coefficient. So instead of this being the damping coefficient, we will start calling it the viscosity when we are dealing with stress and strain. So we know that for an elastic material, stress is equals to elastic modulus times strain. So, for viscoelastic materials, the stress is equal to the viscosity times the rate of change in strain. So if we know the rate of change in strain, and if we know the stress, and we can find a linear relationship between the two, then we have the viscosity of the solid material. Now later we'll be looking at viscosities of liquid materials, which could be defined a little bit differently. We'll come back to that. But for solid materials, this is the model. But actual solids are not always totally uh, viscous or elastic, but they are a combination of viscosity and elasticity. So one way to combine them simply, it's called the Maxwell solid, is to have the elastic modulus and the viscosity in combination in series. So you can get a solid that produce that the data for stress and strain you can try to fit into this kind of model. Now it turns out that it's difficult to fit this model in all cases. So it's usually it's easier to fit data that is contains both a series element, series elastic element, and a parallel elastic element. So let's call it E1, E2, and the viscosity.